Hello, sir. Can you hear me?
Yes, I am able to.
Okay, okay.
Yes.
Sir, good morning.
Good morning. Good morning.
Rekha.
Yes.
I have started meeting and YouTube live also.
Right.
So you can start in now anytime.
Yes. Shall we start now?
Yes.
Okay.
And
Good morning,
sorry, I will be
everybody. Good
leaving.
noon, rather. It's already past 12. So, to
Yeah.
be correct, we should be good noon. Then, this is Arvind Kulkarni from Bangalore. And very happy to welcome everybody for this third and the last day of the Quantum Zoom School of Bharat or India. And today's speaker will be K. Pramod Kumar. I would like to introduce him. Pramod, come on camera, please. Pramod on
Just a minute,
camera.
sir. Just a minute.
Yeah,
Okay. Hello.
yeah. Here comes Pramod.
Yeah.
Pramod Kumar is the head department of physics of BMS College of Women. Did his master's degree in Jain University in Bangalore with fields of interest in optics, electromagnetics, astrophysics, and quantum mechanics. Interest in making models and videos and other activities to make physics learning enjoyable and to develop problem solving skills. He has been doing huge work. He has helped us with many workshops, and he is very young and dynamic, and he connects to the real world in a real way. That is important part about him. He knows the times to come, and that's where I had an opportunity to interact with him and invite him for this particular Zoom program. Since he is a teacher already for 7, 8 years, he should not find it difficult to explain the difficult quantum concepts. He is also interested in quantum mechanics deeply, and I'm sure all of you are waiting for a wonderful session on quantum mechanics or what he is going to do. This session will go up to 12, up to 1:15, and there will be a short break. After that, Dr. Abha Khandelwal will take over. Thank you very much. I leave the stage to you. Yeah, great.
Okay. Thank you, sir. Thank you for introducing me. Can I start my presentation or should I have to
Yeah,
wait for something else?
yeah.
Hello. Can I start?
Yes, yes.
Okay. Okay. Just a minute. Okay. Can you see my screen?
Not yet.
Just a minute, sir.
Yeah, please.
I'm having
Take
some
time.
problem.
Yeah, no problem.
I think I'm sharing my screen. Okay.
Yeah, it is yet, is coming.
Okay. Probably I had to off my video. Okay.
Yeah. Yes, yes. Now,
Okay.
now, now it is shared.
Okay. Okay.
Uh,
So I welcome all of you who are taking part in this today's last lecture. So I want to thank Arvind Kulkarni sir and IAPT for giving me an opportunity to speak to young childrens. So quickly let me go to my presentation about introduction to quantum world and later on and a little bit of quantum computing. So these are the different tools in physics which we use it. So just like we have different tools, we have a hammer to hit a nail, we have a saw to cut a tree, and we have a cutting plier to pull nail, and we have a cutter to cut a wire. So and we have a knife to cut few vegetables. Likewise, we can't have a one rule, one law in physics to study everything. So we have men physicists have formulated different fields, and I am presenting here a few important fields in physics. So which are classical mechanics. Way back in 1650s, Newton gave the principles of Newtonian mechanics, and it deals with large bodies called macroscopic bodies. It was Newton who gave his theories, whose Newton's laws, in Principia Mathematica in 1649 AD, and he formulated his famous Newton's laws. And it was a time where he independently developed calculus. Next, uh, later on in the 20th century, earlier 1900, special theory of relativity was formulated by Einstein. So the main difference between classical mechanics and special theory of relativity is classical mechanics is applicable to only bodies which are moving with very less speed. Okay. The speeds of bodies which are very, very less comparable to the speed of light. For that domain, we have to take classical mechanics only. And for example, for the bodies or objects which are moving with very large velocities, example, electron in an hydrogen atom. Electron in an orbit of an hydrogen atom moves with comparable to speed of light. So for that cases and all, we have to take special theory of relativity. So now our main aim is to study other branch called as quantum. Quantum world goes out is needed to study subatomic particles, very small particles. Just like we have atoms, every matter is made up of atoms, molecules. Every gases is made out of atoms, molecules, liquids. Entire material is made out of atoms and molecules. So atoms and molecules are in turn made out of nucleus. Nucleus comprises nucleons. Nucleons have protons and neutrons. So this nucleus are being surrounded by electrons which move in their own certain orbit. So to study those things which are very small, which are not visible to human eye, probably they are in the realm of Angstrom, 10 power minus 10 region ಅಲ್ಲಿ ಇರುತ್ತೆ. I'm sorry, they are in 10 power minus 10 region. So for that cases, we have to study quantum mechanics. Atoms, electrons has to be studied in quantum mechanics. If I go still deeper, if I go peeping inside the nucleus, I'll go to neutron, proton. I'll get strange particles, elementary particles. For that, I had to study nuclear physics. So anyway, we are not going to nuclear. We are in quantum. Okay. To study small objects like electron, proton, neutron, and gases, we need nuclear physics. So we need quantum mechanics. And what is the main reason for using quantum physics is certain experiments, certain phenomena observed in nature could not be explained by classical mechanics. One of the famous experiments done by Einstein was photoelectric effect. What is photoelectric effect? When a light of certain frequency fall on certain metals, electrons gets ejected out of it. So this is a famous experiment which could not be explained using Newtonian physics or classical physics. Another famous experiment was black body radiation, emission of energy by black body. So many people try to explain it. Wien's law is there to explain it. Rayleigh's law was there. Stephen's law. Various people, various physicists around 1900 tried to explain it, but they could not do it. So then comes Planck. Planck, a famous Austrian physicist, German physicist, Max Planck, who comes out of the box, thinking out of the box, and gives the theory of black body radiation using his quantum ideas. So whenever there is a problem, nature tries to provide us the solution, provided we are in resonance with the nature. So therefore, necessity is the mother of invention. Okay. So a famous quote by another person, another physicist, Austrian physicist by name Niels Bohr. If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. So, the foundation for quantum theory was given by many persons, and one of them is Niels Bohr. He uses certain smaller and easier available elements. He took hydrogen. He wanted to study the various parameters in hydrogen atom. He wanted to study electron revolving, radius of the electron revolving in hydrogen atom. He wanted to know the velocity of the electron revolving in the hydrogen atom. He wanted to know the energy, both kinetic and potential energy of the electron revolving in a hydrogen atom. So, what Bohr did was, he gave his theory independently to explain atomic spectra. Okay, each element gives its own unique spectra, which is characteristic of each element. Okay, so Niels Bohr, with his theory of hydrogen atom, went on to explain atomic spectra. But one of the main unfortunate failure of his theory was he could not explain for larger, heavier atoms. His theory is applicable only to hydrogen and hydrogen like atoms, and which are lighter. So then comes so many other people to explain the problems. So our main aim is to study quantum. So probably here 9th standard students are there, right? Sir, all are 9th standard students, sir. Hello? Hello? Is my voice audible?
Yes, yes. They're all 9 standard students. Very few, maybe 11, but most
Okay,
of them
okay.
are 9. Yeah.
Okay. So thank you. So the main
Yeah.
difference between classical and quantum is, I will show that picture and then come here. See, this is the main difference between classical and quantum. For example, I have taken a car here. A car can have energy within whatever range it wants. Okay. The car can have an energy of say 10 joules. Energy is measured in joules, probably you know it. Car can have 10 joules, 10.5 joules, 10.6 joules, 10.7 joules, 10.8 joules, 10.81, 10.82, 10.83, 10.84, and 10.85. So, car can have any fractional value of energy. Since it is moving, it will have probably, it will be having kinetic energy only. So, a car can have any type of energy, any value of energy. Whereas hydrogen atom, see, I have taken an hydrogen atom here. Sorry. So this hydrogen atom, which is in the first orbit, it is in the first orbit or first shell, we call it as first shell or first orbit, cannot have any value of energy. It can take only few specified energy range. It can have only few allowed energy, allowed orbit. This is what we call it as discrete. Discrete means separate. Okay. Electron in an hydrogen atom, first orbit will have 13.6 electron volt. See here, electron is in, this is the blue color, which is the electron. Sorry. Probably if I am able to write, I will write it just for a second. Just a minute.
You can
Probably,
indicate, that should be all right.
yeah,
Indicate.
okay. I think I cannot write it. Okay, I will try to write, explain like as it is. So electron will be in first orbit. Electron can go to second orbit provided we give energy. Just like you can go to first floor, second floor by climbing or by using a lift. Likewise, I can send electron to second orbit, second floor, third floor, so on. So the main thing you have to learn here is electron can go to second orbit, electron can go to third orbit, fourth orbit, but it cannot go to 1.5 orbit. It cannot go to 2.2 orbit. It cannot go to 3.8 orbit. It cannot go to 12 by 4 orbit. I'm sorry, 12 by 14 orbit, 12 by 13 orbit. So it cannot take fractional values. Orbits have to be whole numbers, natural numbers. It cannot be 1.5, 2.8, 13.485. No, those are not allowed. Only few fixed orbits given by Bohr's quantization rule, Bohr's orbit rule. So only those things are allowed. That's why we call quantum as discrete. Discrete means separate. Just like example I have given here, pen. You want to buy a pen for your exam today. You will go to a shop. You'll ask for a pen. You tell you'll ask or you will go to the shop and tell, give me one pen. So he will give you one pen. You will ask, give me two pen. He'll give you two pen. But you cannot ask for give me 1.5 pen. How can a shop owner give you a 1.5 pen? He have to give one pen, he have to break another pen, and he have to give that broken pen half part of it to you. It will be no use for him and no use for you also. So that is not allowed in quantum world. So quantum means a unit of measurement of information of light, a photon. So quantum lies in discrete world, separate world. And one of the main difference between quantum and classical is classical mechanics we call it as deterministic. That means you can determine what is happening. You can measure the past, you can measure the future. Okay. If you know the information now, sorry, if you know the present velocity, I can find the velocity probably after 5 minutes. If you know the position of a particle, if you know the position of my car, I can find out position later on using graphs, position time graphs, velocity time graphs. I can do this in classical world using Newtonian mechanics, but I cannot measure this position, momentum, so on in quantum world. It is not easy. One of the famous comes here. I will show it. Yeah. So this is classical world. This is a graph. I can measure position, time, so on easily using my Newtonian mechanics, using laws of Newton. Whereas energy levels of hydrogen atom are like this. Probably this is ground state. This is first excited state. This is second excited state. This is third excited state. This is fourth state. This is fifth state. There is no connection between those two states. An electron cannot go in between these two states. Electron cannot lie in between these two states. I can lie in ground floor. I can lie in first floor. I can lie in second floor. But I cannot lie in 1.5 floor. Impossible. Likewise, electrons cannot go wherever they want. Electrons cannot stay wherever they want. Okay, that is the difference between classical and quantum world. Okay, this is one of the famous principle, famous law in quantum. It says that if you know the position very accurately, less precisely you know the momentum. So I will take an atom or I will take an electron. If you know the position of an electron very accurately, less precisely you know its momentum. So momentum, what do you mean by momentum for 9th and 11th students? Momentum is product of mass and velocity. Okay. So momentum is defined as product of mass and velocity. And remember, momentum is a vector quantity. So there are two types of physical quantities, scalar and a vector. Okay. So if I know position very accurately, finding momentum, I will get more error while measuring the momentum. But if I know the momentum very accurately, with high error, I will get the value of position. This is what Heisenberg's principle tell. So if you ask me an example for this, I cannot give example in my real life world because quantum mechanics cannot be applied to macroscopic bodies. Anyway, uh, classical mechanics comes under the domain of quantum world of high velocity and of high density and high temperature, low density and high temperature. So imagine I am running away. So if I am running away, I have momentum accurately because I am having velocity. You cannot find out my position. Why? Every second my path is changing, my position is changing. So imagine I am a thief, I am running away from police. Every second I am running away. So you can define my momentum because I have mass. You can take my mass as some 60 kg. You can take my velocity. Probably I'm running with 50 km per hour. Okay. So you know my momentum accurately now, but you are unable to find my position. You cannot pinpoint my location at a point because I am continuously moving. I am in continuous motion. I am in rapid motion. So you cannot define my momentum, you cannot define my position accurately. So this is the case. Example was me running away from a police. Now, other example. Imagine I am standing at a point. Imagine I am standing at a point. So you can pinpoint my location. You can know my position, X locate. You can locate me very well. If you locate me very well, you cannot find out my momentum. As soon as you locate me, momentum becomes zero. Why? Can anybody answer there? Can anybody talk there? Probably we can. Any children can talk there. If you feel free, you can talk. No harm in talking, if possible. Okay. As soon as you find my location, momentum dies out. Momentum becomes zero because as soon as you locate my position, velocity is zero. At that point where I am staying at rest, you have got my position. You have got my position now. I am in Bangalore. I am in JP Nagar right now. I am not moving. I am sitting in front of my laptop. You have pinpointly accurated my position, but finding out momentum is very less, very zero. It is zero because I am not at all moving. I am sitting. Since I am sitting, my velocity is zero. So I cannot find out my position. So this is a crude example, but when you apply this to electron, proton, so on, atoms, position, if you get the position, you will not get momentum very accurately. If you get momentum accurately, you will not get position accurately. So this is what we call it as Heisenberg's uncertainty principle, one of the foundational laws in quantum world. And what is this H cross? Probably you can go to home and Google it out. I cannot write it on the screen. Please forgive me. H cross is a constant known as Planck's constant. H is a constant. We call it as a Planck's constant. H cross is that same Planck's constant divided by 2 pi. Okay. Probably my aim of this class is not to teach you everything and make you learn everything. Only make to feel inspiring. Only to inspire in the field of physics. Probably to take up physics in your future studies. Probably take your career in physics. Take a career in physics in future. Thank you. So, okay, next slide. So, my topic for today is quantum computer. Okay. So, we want to build a quantum computer. Probably India has already started it. IIT Madras is leading in this. Probably you are in Coimbatore. Okay. Madras is there. IIT Chennai is trying to build a quantum computer. Probably next 5 years we may have it. So probably India has many supercomputers. For example, one example in IITM, Indian Institute of Tropical Meteorology, Pune, we have a supercomputer. In Bombay, TAFR, probably they are having a supercomputer named Param, probably. Yeah, there are many supercomputers. So see, I can assure you that in next 5 years, you will be having a supercomputer in your home or in your hand. How, sir? How can you assure you? Assure. I can assure you because nobody had imagined 20 or 25 years back when I was studying in school, like you, 30 years back, that I will have a smartphone, I will have a laptop, I'll have an internet, I'll be communicating, I'll be taking a Zoom class to you. I had not at all imagined. This was a fiction for me, scientific fiction. Talking to a students in Coimbatore was fiction to me 30 years back, 25 years back. But now it is a reality. So, smartphone, everybody is having smartphone in your hand today, right now. But nobody has imagined earlier. So, technology has improved like anything. See, so I have two definitions for you. If you ask me what is physics, I have two definitions. It is mother of all technologies. That is my definition of physics. So, what is one more definition? Physics is a science which makes impossible possible. So, earlier, whatever all were impossible have become possible because of physics. Okay. So, a smartphone is in your hand right now. Probably another 10 years, the speed of smartphone will increase tremendously and your hand smartphone will act like a supercomputer. I am having a laptop in front of me. I'm having a laptop in my college. I'm having a computer in my computer lab. I'm having a computer in my physics lab everywhere. Those are all ordinary computers. It will be replaced by a supercomputer in the next 10 years. Why? Because technology is improving rapidly, exponentially. So what happens if supercomputer come to your hand? Imagine you are a thief. I'm sorry. Imagine I am a thief. We are all a thief. We want to open a, we want to hack a bank account using supercomputer. Probably I can hack a bank. I can withdraw money and run away. So government agency is there, police agency is there. They want to prevent me from doing it. So if I have a supercomputer, I can do it easily. So what I have to secure my banking networks. Okay, I have to secure my banking networks. So what I have to do? I have to have a quantum computer which is much more powerful than my actual supercomputer. So if only God can give some prizes to humans. God can give us. So if we become equal to God, if my power and God power become equal, we'll become same. So God has to be more powerful always. So police has to be more intelligent than thief. So if he has to be more intelligent than thief, he must have a better computer than supercomputer, which I'm already having. So only better computer, which is much better than your supercomputer, is coming technology is quantum computer. So why we call my computer a supercomputer? See, its processing speed is very high. Processing speed of my supercomputer is 10 power 18. 10 power 1 is 100. Sorry, 10 power 2 is 100. 10 power 3 is 1000. This is 10 power 18 floating point operations per second. This is the calculating capacity of supercomputer. What our human brain? Probably humans can calculate 10 bits per second. Bits mean binary digits. We call it as bits. Bits means binary digits. Probably a very high IQ person. Probably Einstein had a very high IQ. His IQ range was about 180. IQ is measured in by asking few problems and solving it within per second. Einstein had a high level of IQ, 180. So probably today many people may have that much of IQ. So if I have a very high intelligent person, he has 10 bits per second. His processing speed, his calculating speed will be 10 bits per second, not more than that. See how my supercomputer is powerful than a human brain. But what about a quantum computer? It must be very, very immensely large compared to my supercomputer. Now, what is the reason for this computing power? How are all these quantum computers built? How are all these quantum computers built? Sorry. So, do you know who is this? Can anybody guess who is this in the audience? Students? Can students talk? Is it available for them? Can they reciprocate back? Hello? 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 Okay.
Coordinators, kindly help.
Can anybody know who is this in the audience? No problem. If you don't know, just for curiosity case, I am asking. See, he is Gary Kasparov, famous chess player. He's a grandmaster in chess. He had defeated the computer named IBM Deep Blue in 1997. He was the only person during that time to defeat a chess playing machine. So probably he has won four times he has won, two times he has drawn, another two times he has lost playing with computer IBM Deep Blue. So see how what may be his capacity, brain capacity that he has defeated a computer in chess. And anyway, that IBM computer is very old, 1997, almost 30 years, almost 20 years old. Anyway, the technology is obsolete now, redundant now. Now anybody probably, if you try, you can beat that Deep Blue computer. But now, as technology has improved, progressed, we have a another powerful chess playing machine called as Stockfish. We call it as a Stockfish. Unfortunately, no human has beaten that computer. Stockfish computer, supercomputer na, nobody has able to beat Stockfish in computer. And I can safely say, nobody can beat that Stockfish also. You can try n times. You can try 100,000, 1 lakh, 1 billion times. Even if you play 1 billion times, I can assure you 99.99% of it, Stockfish will win. You have a winning percentage of 0.0001. That is large in count of my telling. So why that is more powerful? One of the reason is computers don't get tired. Humans get tired. Okay. Computers are made out of powerful algorithms. They can calculate how much this person can calculate 10 bits per second, whereas my computer can calculate 10 power 18 probabilities, 10 power 18 positions. So when you can think 2, 3, 4, 5 moves per second, whereas that supercomputer Stockfish can calculate 10 power 18 moves per second. So it can predict future. It can modulate, it can simulate your brain, it can control your brain. That means it can assume what moves can you do. We can do 4 to 5 moves probability, but it can do 10 power 18 per second. Okay. What is the reason for such power? Reason for such power is all my electronic devices, all my electronic gadgets are being done, manufactured using by a special material called as semiconductor. So what is a semiconductor? It is a material whose conductivity lies between that of a conductor and an insulator. So conductors are materials which allow heat and electricity to pass through them easily, whereas insulators are those which are not allowing any electricity or heat to pass through them. They are called as bad conductors. So conductors allow everything to pass through them easily. Electrons can flow easily through them. Electrons cannot move through insulators. They are also called as dielectric. Okay. But these semiconductors, one of the main advantage of using semiconductor is its conductivity can be controlled. Just like I can control flow of water in a tap. Just like I can control flow of water in a dam. Likewise, I can control the conductivity. I can increase the flow of electrons. I can decrease the flow of electrons by method called as doping. Probably you will learn your higher classes. So, semiconductor conductivity can be controlled. Something which can be controlled leads to a greater ability. Okay. So, all your computer, supercomputer, laptop, television, speakers, mobile phones are all made out of these semiconductors. And probably in future, we may no longer be able to use this semiconductors. Why? I will tell you in future. So we are in a process of building a quantum computer. A famous physicist, Nobel laureate Richard Feynman coined the term quantum computer along with David Deutsch and Paul Benoff during 1970s. He was the founding father of quantum computing and also nanotechnology. One of the famous statements given out by Feynman was there is still plenty of room in the bottom. How? I will tell you later. Okay. What are all the problems with my supercomputer now? What are all the problems with classical computers? So that we had to discard our computer. So probably in future we have to throw all our laptops and TVs. We'll be having new types of material, new types of display material, new types of diagnostic materials, new type of computing materials. All our just like our old radios. Probably if you go visit your grandfather, if you ask your grandfather, grandmother, or their fathers, great grandfathers, if you ask how was your radio, they will tell that your radio was as big as a tank, over a tank in your school or in your home. Radio and TV was as big as a tank, over a tank, water storing tank in your school and colleges. So its size got reduced as small as possible right now. Its speed got improved like anything. So the reason for them was using semiconductor technology. So probably the present problem with supercomputers are, classical computers are, they are not reversible. For a given input, for a given output, inputs cannot be deduced. And one of the main reason is all my energy which is being given to my laptop, my computer are being wasted in form of heat energy. Okay. So if you check your laptop now, if you check your computer in your right school right now, if you touch it, you can feel a slight heat. You can feel a slight warm out of it. So go and check your mobile while it is charging. While it is charging, you can feel a warmth in your hand. You can feel warmness in your hand. So go and check your TV. Check a TV after a while. After it has run for probably watched it for about half an hour or 1 hour. You can feel heat. What is the reason? The main reason is the electricity which I am sending, the power which I am feeding to my computer, laptop, television, radio, smartphone. Not all the energy which I am sending is being used for running TV or running laptop. If I send 100 joules of energy to my TV or laptop, only probably 20 to 25 joules of it are used for my computing. Rest 75 joules or 75% goes waste as heat energy. So that is the problem with my computer, my TV, my smartphone. energy losses are happening. Energy loss due to noise, energy loss due to friction. That is the main reason. Anyway, we cannot eliminate friction, we cannot eliminate noise, we cannot eliminate heat. They are practically impossible. If anybody probably eliminate heat energy or minimize heat energy, they
तुम
may be
बस
awarded with
सपोर्ट के लिए
Nobel.
खड़े रहना, जैसे ही
Hello?
मैं कर लूंगी तुम आ जाइए।
Any doubt?
नहीं नहीं टाइम, अभी तो टाइम है। खड़े
Hello?
खड़े
Hello, sir. Can I continue?
Yeah, continue. I don't know.
So
Yeah, continue.
if anybody minimizes friction, if anybody minimizes noise, okay, if that is done, probably they are worth to be awarded a Nobel. They are very difficult. I cannot minimize heat. Okay. So let us study about first quantum computer. So first quantum computer was developed in 2011 by D-Wave company. It was a 128 qubit quantum computer. So now what is a qubit? Qubit means quantum bit. It is an analog of classical bit. Classical bit is a electronic signal which lies in 1 or 0. Quantum analog. Quantum analog of classical bit is quantum bit. It is it stays in a superposed state. Anyway, I'll go to superposition if I have time. So it was priced around 70 crores in 2011. Now, if you ask me what is the price of quantum computer, it is much more larger. It is around 5,000 crores. A huge investment is needed. So that's why more research is going on to develop a quantum computer which is much more cheaper. We need technology which is in our hand, which can be accessible to even a common man. Technology must not be a tool for only rich people. It must be accessible to even a poor man. That is what we call it as success of any technology. See the difference between supercomputer and my quantum computer. Supercomputer needs around 2500 kilowatt of power. So unit of watt is power. I guess you know it. So if a supercomputer needs 2500 watts of power, whereas my computer needs only 25 kilowatts. So how much is the difference? So my supercomputer needs 100 times more power to function than a quantum computer. So in a way, my quantum computer is saving energy. So one of the major problem world seeing today is saving energy. So probably have you heard of Stephen Hawking, famous theoretical physicist from England? So he has predicted around 2300 or after another 1,000 years, Earth will not be habitable because of energy crisis, so many problems, global warming. We have to leave this Earth and have to colonize some other planet on this solar system. Probably we have to go to Mars. Anyway, now only we are not having any water. Now we are not having any efficient and any enough energy for cooking, for traveling. So we have to colonize Mars probably. Okay. So energy need is one of the basic problem which we are facing now. We are facing acute shortage of energy. So in a way, my quantum computer can help me. Why? It needs less energy to function. Whatever problem my supercomputer do, my quantum computer can do much using much lower energy. Okay. Okay. See, one of the famous problem posed by Fermat, a French mathematician, he says that any solution. There is no solution of this form. There are no integer solution for numbers x, y and z for n greater than 2. So I can take 3 square plus 4 square is 5 square. This is Pythagorean triplet. You know this. So there are no solutions for this equation if n is greater than 2. If I put n is equal to 3, there is no solution to this. Unfortunately, Fermat has lost, this problem was posed 350 years ago, and Fermat only gave the statement. He left proof to the future generation, and this problem remained a problem for 350 years. The proof for this problem was given only in 1995. So world was not having a solution to this problem for almost 350 years. So whatever computer you can take, I can give you 10 supercomputers. So there are many problems in maths which are unsolved today, but they are still yet true. We call it as conjectures. Conjectures are mathematical statements which can neither be proved nor be disproved with our current knowledge. So you can go and check in Google millennium problems. What we call it as millennium problems. We have a Hilbert 10 problem where there are various millennium problems. No person on this earth have able to solve till today. Probably I'll give you 10 supercomputers, 12, 50. Still it is still we are unable to solve them because it is out of our reach of present knowledge. So probably you may take help of quantum computer to solve them. How my quantum can help you, we'll see it in my future slides. See, humans are all fascinated by numbers. Humans are playing with numbers. Earlier Greeks had a notion that prime numbers are God numbers. Prime numbers were given by gods. This was the notion by earlier Greeks and earlier French people, earlier Latin people. So always there is a search for prime numbers. So largest prime number was obtained in October 12, 2024. It is called as Mersini prime. So this is the largest prime number 2 power 13642798841. If you take power of 2.
Pramod, they
Ah,
wouldn't know how the prime number and computers are connected. So
okay.
kindly tell that, and then you go over.
Okay. So we have used a supercomputer. Probably we have a physicist, a mathematician has used a supercomputer to get this prime number. It has 4102432 digits, and it has taken almost 11-12 years to search this prime number. See, the time, it is not the ability to solve a problem, it is ability to solve a problem with less amount of time. That is what we needed, and our supercomputer fails to solve a complex problem in a limited amount of time. Okay, but if I have a quantum computer, I can solve these types of problem accurately and in a less amount of time. So you have to appreciate the power of quantum computer. We can calculate, or we can estimate, or we can determine, or we can obtain the solutions of complex problems much faster. So how are these quantum computers done? Using a single slit, using a famous experiment given by Young called as double slit experiment. Famous Young's double slit experiment. Probably if I have a video, I will try to show it. I'll try to show it more than explaining it. Just a minute. Okay. Okay. I'll try to show that video. Okay. Probably it may not run in Zoom. Okay, I'll return back. So, I'm unable to share. Why? I'm not able to share my screen. Okay, I'm sharing my screen. Okay. Sorry. So, to build a quantum computer, we want a quantum bit. I told you quantum bit is an analog of classical bit. So, how to get a bit, quantum bit? See, one of the famous experiment given out by Thomas Young tells that electron is a particle. We know that electron is a tiny particle, alva. I'm sorry. Electron is a tiny particle. I am a bulk particle. I am a bulk particle. You are a bulk particle. You are a large particle. Elephant is a large particle. Even ant is a large particle. Snail is a large particle. Car is a large particle. Electron is a small particle. Electron is a quantum particle. Proton is a quantum particle. Light. See, light is made out of photons and they are also quantum particles. Okay. So, when people, we call it as a double slit. I have a two openings in my slit. Okay. I have two opening in my slit and light is made to fall on both the slits. If light is made to fall, light or electrons is made to fall on both the slits, I'll get a interference pattern like this. This is the interference pattern. Probably if I want to run this video. Can you hear this?
No. No sound.
No sound, okay.
We can explain if you like.
Okay. So probably in Zoom I cannot send it. Sorry for it. So now there are two openings here. If I throw two stones out of it, I will not get a pattern like this. So if I send two stones, if I throw two stones or some 100 stones through this, I will not get a pattern like this. I will not get an interference pattern like this. So now imagine instead of throwing stones, I will send electrons. I will send light. If I send a light through this two openings, if I send electrons to this photons to this two openings, I will get an interference pattern like this. Why? The reason is light, as I told you, light is made out of particle called as photons. Photons are not only particles, they exhibit wave-like properties also. They exhibit wave-like properties. So, my light is a wave, my light is a particle. My light is both. Light is wave as well as particle. So, similarly, electron is also a particle, also a wave. Okay? Electron is also a particle and also a wave. Now, instead of sending many electrons, many phases thought an experiment, hypothetical experiment, to send only a single electron. So what will happen if I send only a single electron? If I send only a single electron, it has to pass what people guessed was it has passed through any one of the two openings and enter the screen, hit the screen. But according to it, my electron amazed the physicist. It neither went to any one of the slits, it entered both the slits. Why? How can an electron, which is a particle, enter both the slits? See here, I cannot study Young's double slit experiment using particle characteristics. I have to study this experiment in wave nature. So electron passes both the holes, interferes after the slit, and I get an interference pattern. So this is an interference experiment. Now what will happen? Now people were more brilliant. Physicists thought I am more brilliant than the electron, and they thought to place a microscope here. Since electron is small, I had to place a microscope. There is no microscope to see an electron. It is a limit. Heisenberg's uncertainty principle limits any microscope. There is a microscope named as gamma ray microscope. Even using gamma ray microscope, we cannot see an electron. Least we can see is an atom, layer of an atom using X-ray diffraction. Okay, least we can see a layer of atoms placed. We cannot see an electron. So people, out of curiosity, physicists out of curiosity, kept a microscope here and they wanted to see through which hole electron passes. They wanted to see through which hole electron passes, but to amazement, electron did not pass through any hole, did not show interference effect only. So electron did not pass through any hole, it did not pass like a wave, it passed through both the waves and I did not get a pattern, interference pattern in the screen. So if I see an electron as a particle way, I will not get an interference pattern. So I have to see this experiment in wave nature only, wave only. Okay. Okay, sir, I'll finish off in 15 minutes. Okay. Okay. So why when I saw an electron as a particle, I did not get a pattern. When I see electron only as a wave, I see interference pattern. It is the same electron. Once it shows the pattern, other times it doesn't show the pattern. What is the reason? The reason is its quantum nature. Its peculiar nature is because of its quantum nature. That is, in quantum world, measurement always disturbs the system. When you measure something, its wave function collapses and you will no longer be in the quantum world. You'll go into the domain of classical world. So measurement disturbs the system. Measurements destroys the system. Measurements destroys the quantumness. Okay. So I have to study quantum physics in terms of, I have to study electrons, subatomic particles in terms of quantum nature only. I cannot apply classical term in this. And if I have to study quantum, computers, just like there are in classical computers, I have semiconductors. I have integrated circuits. I have various circuits. I have various connections. So I need gates. Gates are some circuits made in classical, in electronics. So I cannot use those gates in quantum. I have to use separate gates. They are called as quantum gates. So one of the main advantages of quantum computers are the gates which are used in quantum computers. Here, number of inputs is equal to number of outputs. Whereas in classical computer or in a supercomputer, inputs are large, outputs are less. See, inputs are large, outputs are less in my ordinary computer, in my TV, in my smartphone. I am giving many input, I am giving less output. Why? What may be the reason? I am giving many inputs, but I am giving less output. Where are the other inputs gone? Other inputs are wasted in form of heat energy. So this I have told you earlier. My inputs are lost, my informations are lost. They are lost forever in terms of heat, light, sound, so on, noise, etc. Whereas there is no problem of information loss in quantum, because here whatever the input you give, you get same output. There is no scope for loss of heat, because one of the main reason is quantum computers work in very low temperatures. Very low temperatures, friction can be avoided. Okay, at very low temperatures, friction can be minimized. At very low temperatures, electron can tunnel easily. There is an important concept called as quantum tunneling. Okay, at very low temperatures, electron can form a Cooper pair and move easily. That is called a superconductivity. So no information is lost in quantum computer. So why do we need a quantum computer? That is the reason. As I told you, the power of my supercomputer is due to the number of transistor it has. Imagine a pen. Probably if I'll try to show a pen. Okay. Can you see me? Hello?
Yes.
So can you see the pen?
Yes.
So you see my pen, it has a refill. So there is a tip of my pen refill. On that tip, you can place 10 billion transistor as of now, as of today. As of today, you can place 10 billion transistors. More the number of transistors, more is the processing speed. Okay? But what happens as you go in the future, there will be a limit where you no longer can increase the number of transistors. So there comes a time where you cannot build more transistors. You cannot keep more transistors in my integrated circuit. So if there is a limit to my placements of transistors in a circuit, my speed gets limited, my speed gets reduced. My computing speed will hit a roadblock. My computing speed will hit a dead end. No longer we can improve my speed. So what happens? I had to find a way to improve my computing power. Then there comes quantum computers. So there is a no limit for computing power of quantum computers. They are very, very much stronger. If I have time, I can show you the power of quantum computer. See, this is how number of transistors has increased. In 2021, we have reached 15 billion transistors now. Today, on my pen tip, I can place 15 billion transistors. Probably in another 5 10 years, it will stop. I cannot place my transistors. So my supercomputer will not have any more power to speed up the calculations. Okay. So the only solution is I had to go for quantum bits. So what do you mean by quantum bits? So classical physics, this is quantum physics. I told you earlier. Let me go further. I have less time. But there is a problem in quantum bit. In order to have a quantum bit, I need qubits to be in coherence. I want my qubits to be in superposed state. My qubits have to be in superposed state for a long duration. This is the quantum computer which I am showing you. This is the quantum computer of IBM. in California, quantum computer in MIT lab. Okay, so in order to see that my quantum computer works properly, all my qubits have to be in a superposed state. So this is a quantum term. We call it as a superposed state. In order to make sure that my quantum computer works properly, all my qubits have to be in coherent state. I don't have a board. I cannot show you what do you mean by coherence, constructive interference, destructive interference, so on. Okay. So decoherence makes quantum computer to lose its power. So I have to make sure that my quantum computers does not experience this decoherence. As the number of qubit increases, the influence of the external environment perturbs the system. Perturbation means other external factors. This causes a state in the computer to change in a way that it is completely unintended and unpredictable and rendering the computer useless. This is called as decoherence. We had to make sure that our quantum computer may not experience this decoherence. Okay?
1 minute.
Yeah.
Pramod, we need to explain the coherence and the decoherence.
Okay.
Coherence simply for the audience.
Yeah.
Coherence means supposing look at my two hands. Look at my two hands. Okay, if my hands are moving together perfectly together, then I say that my two hands are moving coherently. Coherently. When my two hands do not move together, meaning like this, then they're incoherent. Then the movement is incoherent. See here. If they move together like this, then they are coherent. If they move up and down, differently, not knowing each other, then it is incoherent. Coherence and incoherence simply mean that if you have seen a set of birds flying in formation, they know perfectly when to flip the wings up and down because they have to flip the wings up and down together so that their whole the group of the birds moves together in together. That is in a formation. It's called formation flying, similar to the aircrafts and other things that they do in this military shows and other things. But I'm talking about the birds. Okay, so when the birds need to fly in formation, their wings need to flip or coherently. Otherwise, if it's a single bird, it doesn't have to bother. Thank you.
Thank you. Oh, I can give one more example for coherence. Probably you have seen a Republic Day parade by army people or
Yeah.
your school parade. There, army people, Republic Day parade, Independence Day parade, there, all the legs kept by the army people will be in same way. No two people will put the legs improperly, right? That is an example for coherence. So if some of them put their legs improperly, we call them as decoherence. So decoherence destroys the quantum computers, destroys the capacity, destroys the quantumness of the computers. So what I have take care, I have to take care that they are not in decoherence. So one of the way to keep them in coherence is we have to go to a very low temperature. So very low temperature, approximately 10 millikelvin. See, 1 Kelvin, we know conversions between degree and Kelvin. If my room temperature is 30 degree now, I don't know the temperature in Coimbatore today. If it is in 30 degree, if it is 35 degree in Coimbatore, 30 degree, then you have to add 273. So Kelvin, it is 303 Kelvin in Coimbatore. So likewise, it has to be 10 millikelvin. 10 millikelvin means 0.01 Kelvin, approximately close to zero, absolute zero temperature. So in that absolute zero temperature, my qubits will remain in coherent state. They will be in superposed states. So these are the hardware needs of quantum computer. So probably I'll stop my presentation now Probably this is the time which I have given to me by sir. So over to you, sir. If there are any questions, I will be happy to answer. Probably I have reached the students. Anyway, it is. If they have any talk, they can contact me later on also. Over to you, sir.
Please share your slide, the first slide where your email and number were there.
Okay, I'll share this to Kulkarni sir. In
Yeah.
turn, he'll share it to the students later on there.
Yes.
Okay. Thank you. Any students? I'm ready to answer by students. Any else? Anybody else? The main disadvantage is interaction is less in online. Okay. Any questions?
Coordinators, kindly check if there are any questions so that we can.
Audience students, any questions? You can feel free.
You can give your questions in writing also to a
Yeah,
coordinator. They will share with us.
you can write it also. Students, if you have any question, you can share it to your teacher. They can contact me later also. Okay. I'll share my PPT to sir. Probably he'll share it to you. You can contact when you need it. Chess player name is Gary Kasparov. He is a Russian chess player. Famous chess player who has beaten the computer not once but twice. Yes. Any questions? Any else? Any other questions?
Okay, if there are no questions, we will thank Professor Pramod for his wonderful presentation on quantum computers today. He has given a lot of information, and I'm sure students will like to learn from it. And now there will be a break for 5 minutes, and then we will have Dr. Prabha Khandelwal, who is ready. She will take over. Please come in 5 minutes. 5 minutes break should be more than enough, we think. So please ease yourself a bit and return after 5 minutes. Thank you very much.
Thank you.
Exactly 5 minutes. 5 minutes means 300 seconds, not more than that.
Thank you.
Uh, I have given a quiz on Pramod's classes, so you please see these 15 questions or 20 questions and answer. Let the students write it, and after another half an hour, I'll be sending you after 1 hour also, I'll send you the solutions to this. Thank you. I was requesting for a 10 MCQ quiz question so that I can share with the coordinator. Thank you. Yes, kindly return. Kindly return to your seats.
Sir, please make me co-host.
Yes, yes. Kindly return to your seats. Is everyone back? Is everyone back? Yes, please join back to the program. Okay, return to the, yes. I wish to introduce, I wish to introduce Professor Abha Khandelwal. Abha has been teaching physics and computer science for the last 35, 40 years. He has been an excellent communicator of physics as well as computer science. And yeah, she will start the presentation now. She will start the presentation on quantum cryptography as a field, and let us start with the same. Let us start. Yeah, go ahead. Yeah, Abha will start.
Thank you, sir. Yeah.
Sorry,
Thank
I
you,
could
sir.
not introduce it properly. I had some problem here.
So please make me co-host.
Yeah. Yes, let us start.
Sir.
Can we start now?
Sir, it is not letting me
You're not letting.
share my screen. Yeah. Host disabled, participants is screen sharing.
There is something going wrong with my end. Something went wrong with my end. Is Geeta there? Geeta ma'am?
Sir, since you are the host, I'm sure you can make her the co-host.
Yeah.
You are named as host only. So please press on her name in the participants list. Maybe that option will come to make her co-host.
Okay, she's the co-host. Yeah.
You have to make her as the co-host.
I have to make her co-host.
You open the participants list, press on her name, probably you would be able to make her as the co-host.
I'm not able to do it. I have problem connecting. I don't know how to make the person a co-host. Can you go back, madam?
Allow participants to share screen. That can be given.
Yeah.
Now probably she would be able to do it. Now, madam, are you able to do it?
Yes.
Okay.
So I am audible.
Okay.
Namaste, students.
Okay.
I want to hear from you.
Yes, I'm able to hear.
Okay. So let us start with session 3, part 2. This session is all about the application. So quantum cryptography we are going to learn today. What is cryptography? It is a science of securing information. It ensures that the data, a message or a password or any financial data, it should be kept private and protected from unauthorized access. Why? You know very well, we cannot leak our password. We never would like to get anybody to whom we do not want to give access should read our messages, and financial data is, of course, to be kept secured. So the cryptography is the science which gives us technology, which gives us methods for keeping our data secure. This is not new. It didn't begin with our computers era. Since years, all civilizations were using secret key. So Rajas, they used to send in code words, the messages written in code words, and then the receiver used to decode them and read it. So that the information sensitive information which is to be passed on should not get leaked. Now comes the classical cryptography, which is also called as traditional cryptography. Now it gives us the facility to secure our messages by transforming them into unreadable format. Unreadable format is a format which others cannot read. Only the receiver can read it. How do they do this? Using mathematical algorithms. Now, in this process, two steps are involved. One is encryption, another is decryption. Encryption is the process of converting a plain text into ciphertext using a secret key. And then decryption, it converts ciphertext back into the plain text using the same or related key. So we will take one example, substitution cipher. In this Caesar cipher, to encrypt each letter in the message is shifted. Each letter in the message is shifted by fixed number of places in the alphabets. And to decrypt, these letters are shifted back by the same number. That is the key. Let's see an example. Now, in this example, let us shift each letter by 3. You are very much familiar. Even nowadays, I have seen very young students, kids, solving this type of puzzles. So I am giving you a word, hello, and just shift each letter of this word by 3. So H will become IJ, K. So H will become K and so on, so that you can do. Would you like to do it on your own? Will someone come with answer? Okay, no problem. Let us shift it by 3 and you will see that the cipher text will be KHOOR, KHOOR. The actual message which you want to convey is hello, but instead of that, the receiver is reading KHOOR. So at his end, because you have encrypted your message, so this encrypted message needs to be decrypted. And how that is done? Decryption means you shift letters back by the same numbers. So 3 we have chosen. So we will have to shift KHOOR back by 3 letters. And each and every letter letter of this alphabet, you have to shift back by 3. So again, you will get the plain text that is hello. So this is all about classical cryptography. Now, look at this picture. It will give you a clear idea. This is your plain text key you have applied. This becomes your applying encryption algorithm. Now sender sends the converting with the help of key, the plain text get converted into ciphertext. Now in ciphertext, through this channel, now at the receiving end, using another key B, because now you are operating in reverse direction. So another key B applied on your ciphertext, which will get converted back into the plain text. And of course, intruders are always there. Mischievous people are always there, right? We cannot get rid of them, right, bachas? So if an attacker intercepts the key or guesses it, the entire system becomes insecure. And therefore, we have to think about something else. Now, as just now, Pramod sir has very nicely explained you that why we need quantum computers. So that limit of adding on, but how much you can add? There is a limit. Suppose you're sitting in a classroom which has capacity of 30 and there are 30 students standing outside your class. Can you accommodate them? Even 10 you can't accommodate because each one has occupied one seat. So there is a structure. Beyond that structure, you just can't go beyond. You just can't overcome it. So we have a limit, and with all those limitations, then we jump to quantum computers, which is incredibly fast and powerful. It can solve problems in seconds that would take traditional computers millions of years. Sir has given you example that how long it took to compute the factorial of that big number. 11 years, 12 years, what is this, right? When we think of a computer, we want just immediate result. Then only we say, yes, then we are working on a computer. But of course, the task is big, so definitely it will consume more time. But all those tasks which were taking such a large amount of time, they are getting solved in seconds using quantum computer. This means the secret code which we were using or we are still using in classical computers, which are designed using classical cryptography, are no longer safe. As soon as the quantum computers will come they will take their place in the market, in every household, everywhere, then they will start attacking your classical computers like anything. Classical cryptography is bound to fail there. So, because it can easily crack these codes, rendering them useless. That's where quantum cryptography stepped in. So I hope you are comfortable till now. And I would also like to, just giving example, I would like to make you very clear that what is the difference between your classical computer and the quantum computer. Superposition, that also sir has covered, that superposition of both 0 and 1 is a quantum state. So superimposed position mein, the 2 bits in classical computer, how can you represent them? 4 state, if 2 bits are there, 0 and 1. Kitna combination hoga? It will be 0, 0, 0, 1, 1, 0 or 1, 1, right? But only one of them will be entertained at any point of time. So while executing one by one, these states will be treated. Whereas in quantum computers, the 2 qubit, they will represent the exact same 4 states. Which 4 states? In quantum also, there are bits on machine can understand only 0 and 1, nothing else. Don't think that quantum computer is a magical thing which can understand any other digit. No. Machine means machine. It can understand only the language of 0, 1. Whenever we write our programs in high level language, which is understandable easily to humans, they are to be converted using compiler or interpreter. And what do? They convert these high level language programs into machine level language. And machine language means it is a combination of 0, 1, 0, 1. That means you can write any letter on your keyboard, can be any word can be converted into machine language, the combination of 0, 1 string. So now, where is the difference? The quantum computer 2 qubits, I'm saying, will represent exactly same 4 states, 0, 0, 0, 1, 1, 0, 1, 1. Then why should we be so much fascinated and mesmerized with quantum computers? Here is the difference. Superposition. All the qubits, they can represent all 4 at the same time. So in classical computer, they are going one by one, they are treated. In in quantum computer, they are superimposed. So all of them, they will be executed at the same time. That's just like having 4 regular computers running side by side at the same time. Now,
Yeah.
okay. What went wrong? This is what I wanted to explain. This I have explained. Now see, with example, we will try to understand this, that if you add more bits to a classical computer, then what will happen? It can still only deal with one state at a time. But when you add qubit in quantum computer, the power of your quantum computer grows exponentially. How? 3 qubits. It will give you 2 to the power 3, that is 8 states. And there now 8 states at the same time, and in classical computers also 8 states, but one after another. 4 bits at a time, in one go 16 qubits. And there all of these bits, all these states will be entering one by one. So as the suppose 64 bits qubits quantum computer you are making, then these many possibilities are there of carrying out the execution in one go. So that's about 1 million terabyte. It is creating wrong. Okay. Now, I hope you got the difference between quantum computers and classical computers, and all other differences sir has already covered. Now let us jump to quantum cryptography. So first of all, who introduced quantum cryptography? So though we are going to learn BB84, which was Bennett and Brazzard in 1984. They introduced quantum cryptography. Okay, but initially in 1968, Stephen Weisner of Columbia University in New York introduced quantum cryptography, but no one was knowing it, and his paper was rejected by none other than IEEE. So then in 1984, they brought it up, and then it was accepted and it did miracle. Now, how did they start? They started like photons. When they came to know that, sir has already told you, right? That the tiny particles, electrons and photons, in quantum cryptography, BB84, they have used photons. So photons can transmit information. Building upon this work, when they came to know, they realized, one was computer scientist, other was physicist. Both of them realized that yes, we can make use of photons for transmit information. Then why can't we design a secret key using photons? So this is how Bennett and Brazzard in 1984 proposed a method, and by their name, luckily they started with BB. So BB and 1984, they took 84 from there. So this method is known as BB84 for secure communication. Now, in this, they utilize the strange and amazing properties of quantum physics you have learned till now. such as superimposition and entanglement, to create unbreakable codes. So I'm not going to give you the examples of entanglement, but just I would like to explain you at this particular point that entanglement is something you are tuned. If something happens to this, immediately gets reflected here. So they are entangled. These two photons, these two qubits are entangled. So whatever changes are making place in this qubit state, same will be reflected here. So this is entanglement. So they used these properties, and quantum cryptography ensured that our secrets remain safe even in the world with quantum computers, because it is not going to happen like when quantum computers will come and we are going to throw all our classical computers. No, we just can't, because it will take many, many years to bring the cost down. That is really not possible in near future. So we will have classical computers, we will be working on them, and now we can make our classical computers safe with the quantum cryptography, so that quantum computers, they can save their computers by the attack from quantum computers. So it is not just a solution, but it is a future of secure communication. Now, quantum cryptography differs from traditional cryptography systems like classical, because the quantum cryptography, it relies on physics principles, quantum mechanics principles, and rather than mathematics. And you know that classical cryptography solely depends on mathematical algorithms, and it utilizes principles of quantum mechanics to secure communication and protect sensitive information. So it is something like this. And now, as I have already briefed you, that BB84 protocol method is protocol. Don't get confused with the word protocol. We call this, in computer science, we call this as a protocol. We do not call this as a method. Like protocols are nothing but they are also set of codes only. But when we write a program, we call it as a program. But we write a big program, we call it as a software. So the definition changes. So it has its own definition, but ultimately it is nothing but a method. It uses photons to transmit data over fiber optic wire. Now, what is a single photon? Single photon is nothing but a very tiny amount of light. Very tiny amount of light, that will be a single photon. The photons can be oriented, or we can say polarized in specific direction. So this is a property that you can make your photon oriented in any direction. Okay, so they can be oriented, or which we call as a polarized in physics, in a specific direction. So thus qubits can be implemented. Because of this, qubits can be implemented using polarization of a photon. Because with polarization, we will obtain two states. Out of two states, we are going to say this is my zero, binary zero, and this represents my binary one. So this is how the photon is going to be used. And that we will see just in next slide. Now, how do they make this state? So there is a polarization filter, which is also called as polarizer. So using polarizer, you have to polarize. Now, each photon, it represents a qubit. The quantum qubit must have two distinct states. One representing 0, the other representing 1. It's all play of 0, 1 in computers, right? Look here. And I hope till now you are comfortable and you don't have any doubts. So please be attentive and let's enjoy. So the BB84 protocol model, it uses 4 polarization states. How many? 4 polarization states. One is vertical. See, this is vertical, then horizontal, then 45 degrees, and 135 degrees. I repeat, it uses 4 polarization states. horizontal, diagonal, vertical, anti-diagonal. Or you can say 0, 45, 90 and 135. So there are 4 states. Now basis. I'm not going to use the word polarization states again and again. Now whenever I say state, it does mean that polarization state. Am I clear? Okay. Now let's go to these bases. So there are only 2 bases. Please remember this. Okay, then only you will be able to solve problems and you will be able to make keys, your own secret keys, right? And then later on you can play among yourselves. So there are 2 bases. One is rectilinear basis, this. And another is diagonal basis. Diagonal basis is this. Rectilinear basis, diagonal basis. Got it? So there are 2 bases. And for BB84 protocol, polarization of 0 degree on rectilinear basis. Where is 0 degree? This 0 degree on rectilinear basis and 45 degrees in diagonal basis. On just a minute. Polarization of 0 degree on rectilinear basis and 45 degrees on diagonal basis, they are represented by binary 0. And polarization of 90 degrees in your rectilinear basis and 135 in diagonal basis, they are represented as 1. So I will have to make corrections here, but please don't get confused. So let us see here. These are your photons. They are polarized, right? How beautiful are they looking, right? So which is this? Coordinator madam, can you unmute yourself and let the students shout so that I can hear them? So just, can you do that? Now, which one is this? This is which polarization? Vertical, horizontal, diagonal or anti-diagonal? This is vertical. Now this is vertical, that means it is representing 1. This is diagonal. Now diagonal is representing binary 0. So it will represent 0. This is horizontal. Horizontal also represents 0. So this is representing 0. And this anti-diagonal. Now anti-diagonal, so this is representing 1. So this is how they are being represented by binary values. So these are the binary values attached to them. So just because we will work on this only, so let me first again revise it in very short, in a minute or less than that. So we have 4 photon polarization states, and they are horizontal, diagonal, vertical, anti-diagonal, or they are also can be called horizontal, then 45 degrees, vertical, and 135 degrees. Out of these 4, there are 2 rectilinear bases, 2 bases. One is rectilinear and another is diagonal. So these bases we have taken. This is our rectilinear basis and this is our diagonal basis. Fine. And then we are coming to photon, that how to assign values. So these photons, if they are in this direction, that is vertical, or they will be in 45 degrees or horizontal, or they will be in anti-diagonal or 135 degrees. So if this is so vertical, then it is 1. If it is 45 degrees, then 0. Horizontal means 0 and 135 means 1. So this is how the values we have assigned. Now, these photons are polarized with respective polarizers filters. Madam, please switch on your, please sir, ask madam to, put camera on. At least I can see students. Chitra madam, can you please put your camera on? Anyone, please keep your focus. I mean, at least I could see bunch of students on the screen. So these photons are polarized with respective polarizers filters. Polarized photons are transmitted to receiver. Now all these polarized photons, they will get polarized, and in all 4 states they can get polarized, and one by one the photons will get transmitted to through this quantum channel, which is fiber optic cable, and here at the receiving end they will be received by the receiver. Now there is a photon detector which will measure your photon and will detect its mapping their state. So they are to be measured. After receiving, they will be measured, and as soon as you measure them, they get collapsed, and then they will be either 1 or 0, that is classical state. So before collapsing, photons are in superposition state, hence till they are not measured, the result is still uncertain, and therefore they are totally secure till they collapse. So this is how they will be transmitted. But in quantum cryptography, they have done a very nice thing. Instead of saying sender and receiver, for quantum key distribution from one end to another end, they have taken 2 entities, and one is named as Alice, and Alice is your sender. And Bob is at another end who will receive your photons. So they want to share a secret key, the secured key, Alice and Bob, for communication. And using QKD, they exchange qubits to create their shared key. How? Look here. This is your Alice. This is your Bob. Alice and Bob. Now, what is Alice doing? Can you see? Alice has polarized her photons. So these are the 4 states in which she can send the photons after polarization. So she is sending photons. She has not decided any key. She just randomly go. She is going randomly. So she wants to send 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1. This key she wants to send to Bob. One by one, it will reach to Bob. Fine, got it? Now these bits, but again, when 0 is there can be D here, diagonal, or 0 for rectilinear. So again, some uncertainty there. It's not fixed that whether she is going to send this D by using rectilinear basis or diagonal basis. Whatever she is doing, you can see, tadak, 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 she will do like that. So she is sending randomly D, R, D, R, 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 D, D, R, like this she is sending. So, because she wanted to send this, so for she can't send this now. These are the values assigned to these states. So actually she is sending these polarized photons. Okay, for making you understand, we are writing here, these are the random bits which have been sent by Alice. But actually she has sent these photons one by one, and with their states and the basis. States of their states and the, just a minute. So with their states and the basis. So this is the basis, this is the state. Now you tell me, if your basis is D, diagonal, and the state is 45 degrees, what are you sending? You have just learned 0 or 1. Unfortunately, I can't interact. I can't hear voice also, but anyways, I'm assuming that you have understood and you must have answered 0. Then this is vertical, rectilinear, vertical. Do you remember? It is 1. Vertical is always 1. You can remember like this. Vertical 1. We have given, and therefore this is most popular. That we always give vertical 1, horizontal 0. For this and this, you can change. Many a times people give this as 1 and they treat this as 0. But in our example, we have taken this as 0 and this as 1. Okay. So I will show you like this. this. Fine. So now for second, R and vertical, that means 1. Then D and anti-diagonal, that is also 1. Then R and horizontal is 0. R and vertical is 1, and so on. I hope you got it. Okay. Now, what will happen when Alice is sending this? So at the receiving end, this detector is there. Now Bob is there. He doesn't know. He has to collect all the photons. So he will try to measure the state, and he will also use 2 bases. Now, which basis? This one, rectilinear or diagonal? He is confused. Which one to apply? He will have to guess. Alice ने क्या भेजा? Alice ने तो D भेजा, right? The first photon को उसने D से भेजा. So instead of this, if Bob uses this for measuring and taking it for measurement, then definitely he is going to receive the wrong qubit. So this will be wrong qubit. But if he receives the same D, then fine. Now, this way, now we are just assuming that Bob's measuring basis is this, R, D, irrespective of this. But he doesn't know anything. He is blank. He is applying just randomly. जैसे उसने randomly भेजा, Bob is also doing the same. So R, D, R are just trying to guess and making assumptions, and he is trying to control. Now, what will be the values received by Bob? Now, Bob, R1 is received by Bob. Here 1 he has received. Here also, yeah, 0, 0, 0, like this Bob has received values. Okay. Now, when Bob receives these values, then what will, after that, once Bob has received all the values, then they will openly share the basis. They will openly share the states, polarization states. So they are not afraid of anything. So they will share that I have sent these bases, R, D, R, D, D, R, R, D, 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 R. Okay. So this is the Bob ने report किया किसको? Bob has reported to whom? To Alice. Bob has reported to Alice कि उसने कैसे receive किया? Alice asked him, what you have received? So he is replying, I have received first proton तो उसने मिला ही नहीं उसको, वो loss हो गया. Second one D, third R, fourth D, like this, and then again some missing are there. So in whatever sequence he has received, he will narrate that. Now Alice बताएगी इसमें से, she is not going to tell the correct sequence. She will only tell that which he has received rightly. So she will say, okay, this you have received rightly. This photon has been received rightly. This also, this, and this. So these are the correct bases which you have received. And now they will try to match. Now matching will happen. So wherever the whole information which was 1D was transmitted, D1 was received, 1R transmitted, R1 received, 0R transmitted, R0 received, 1D transmitted, D1 received, 0D transmitted, D0 received, like this. So whichever values matches, so they will become your shared information. This will be your key. 1, 1, 0, 1, 0, 1.
Yes.
So this is how it works.
Yeah, shall we stop now? It's 2:10.
Oh, sir.
Shall we stop
Sir,
now?
just
2:10 is over.
eavesdropper.
You have something to conclude?
Sir, can you? I will cut, but only eavesdropper ko ला दीजिए. Without that, it will be. So what if your malicious attacker Eves tries to measure these quantum states in transit to gain information about the key?
Yes.
Now Alice is there, Bob is there, quantum channel is there, photons are getting transmitted, no problem. But there is one introducer, Eve. She is trying to peep in. She is trying to get the information. So will Eve be successful? In quantum cryptography, I will just explain you with this example. As now see, this is your rectilinear basis. Bob has also measured it with rectilinear basis, but she is trying with diagonal. So she fails to get the information about this photon. Another photon she is sending to diagonal. This time your Eve is right, but Bob is wrong. So if Bob is wrong, so when they will tally the basis, right? They tally the basis after completing the process of transmission. They will tally the basis through communication via mail or via phone, whatever. So here they are they are tallying using phone. So now you can see that he is wrong. So automatically this will get discarded. This won't be counted in a key. So Eve is going to fail. And there are many more reasons, but at least if you can understand this much, this is more than enough. So I hope you enjoyed this session a lot. And just for a minute, applications. They are used in government. They use for classified communication. See, in military, it is very important for secure communication. In financial institutions, they have started. Healthcare also wants their medical records, because they are very highly sensitive, to keep secure. So quantum cryptography helps in maintaining the privacy of these records. So I wanted to give you this exercise, but anyway, we are short of time, so I will tell you the answer. It is 1-0.
Yes.
No problem. Okay. Thank you. Thank you, sir.
Great. Thank you very much, Professor Abba. It was a great session indeed. It was great. I myself was not clear about many processes, but now things are getting clearer and clearer to me. Okay, and I'm sure all our young audience all over the country will definitely be benefited from it. Okay, I had some difficulty in the second part of it, but now I'm back here. With that, I would like to thank Professor Ava first for her wonderful presentation and beautiful slides. I will appreciate if you can share the slides with me later so that I can go through them more thoroughly. Uh, Also, now it is already 2:10, and I don't think students would like to stay longer for various reasons.
Yes.
So let me thank all the participants from across the country, along with their coordinators and schools that helped, and of course all the speakers. We had four speakers, including Dr. Abha Khandelwal. I thank everybody, and I thank IIT Central for giving us the platform. With this, I declare the session closed and the program closed. The 3-day program was wonderful, and I request you to send me the feedback in various forms so that we can compile and make a better presentation. Thank you very much. Thank you.
Thank you, sir. Thank you.